Okay. We are still looking at logarithms. Up until today, you guys have learned how to solve a logarithm, and you've also learned how to change between logarithmic and exponential form. Today, we're looking at how to solve equations that have logarithms in them, and there's some properties that we're going to look at. The first one says this: if log base 5 of x equals log base 5 of 8, if log base 5 of x equals log base 5 of 8, then what does x equal? What do you think? The logarithms, sort of. Just comparing these two logarithms. Yes. X equals 8. So the property is, if you have two logarithms that are set equal to each other, as long as they have the same base, then whatever is here and here must be equal. So in order for these logarithms to have the same value, because they have the same base, the x has to be equal to the 8. We're going to look at some examples. Example 1, log base 2 of x squared minus 4 equals log base 2 of 3x. Then a lowercase l. Okay. So what we have is two logarithms that are equal to each other. Because they have the same base, we know that x squared minus 4 has to be equal to 3x in order for those two logarithms to have the same value. So to solve this, we're going to just do that. X squared minus 4 equals 3x. So we basically use the properties to get rid, or the property to get rid of the logarithms. So now we can solve this equation for x pretty easily. Well, fairly easily. Because we have an x squared term and a term that just has x to the first power, that should tell you that you're going to have to factor this in order to solve. So hopefully you remember factoring from last year. A lot of you put that on my Google form that said, what's one thing you remember from last year? A lot of you put factoring. So I'll give you a little crash course reminder if you don't remember, but in order to factor a quadratic, which is what this is because we have x squared, you have to get everything on the same side of the equal sign and have it be set equal to 0. So let's subtract 3x from both sides. The reason we subtract it is because it's already positive and we want to move it to the other side of the equal sign. To move it to the other side, you have to do the opposite of what it already is. So because it's already positive, we subtract. So what we end up with on the left side is x squared minus 3x minus 4 equals 0. Okay, when we factor into two sets of parentheses. Remember? What goes at the front of both of these sets of parentheses is x. Sorry. It's the a square root of whatever your first term is. So our first term is x squared. The square root of x squared is just x. That goes at the front. Then we're looking for numbers that multiply to be -4 and add to be -3. Multiply to be the last number, add to be the middle number. So what are two numbers that multiply to be 4, -4, and add to be -3? 2 and -2 would multiply to be -4, but when you add those, you get 0, and we need it to add to be -3. 4 and -1. Okay, if we do, that will multiply to -4. 4 and -1 is going to give us a +3. Yeah, -4, +1. Which, that's the exact work that it takes at that spot, is to just think of factors of 4, do it in your head until you find the one that works right. So, good job. Okay, after you have your factors, we set each factor equal to 0 separately, because in order for these two factors to multiply together to be 0, one of them would have to be 0. And now we just solve each of these equations for x. So get x by itself. Add 4 to both sides to get x equals 4. And subtract 1 from both sides to get x equals -1. You can pretty much skip this step right here if you wanted to, because if you just look at the factors, you know that x is going to be equal to the opposite of this sign. So if you have x -4, your answer will be x equals +4. If we have x plus 1, your answer will be x equals -1. So if you want to skip this step here, you can. That was a bad arrow. But that's up to you. You can always definitely do this step too. Okay, we have two answers for x. We have x equals 4, x equals -1. Because we're working with logarithms, we do have to go back and check to see if these numbers are actually solutions to this equation. So we're going to check x equals 4 by going back to the very first line of our problem and plugging in 4 for x. So we have log base 2 of 4 squared minus 4 equals log base 2 of 3 times 4. Oops, sorry. We're checking x equals -4. Okay, let's do this little bit of simple math. 4 squared is 16, minus 4 is 12. And 3 times 4 is 12. So when we use our property that we're learning, because these logarithms have the same base and they're set equal to each other, we know that 12 has to equal 12, and it does, right? 12 equals 12. That's a true statement. So when we checked x equals 4, it worked out. That means x equals 4 is a solution to this. I'm going to circle it. So circling it shows that not only did I get it as an answer, but I already checked it to make sure it's a solution, and it is, so I'm circling it. Now let's check x equals -1. So back to the very first line of the problem, plugging in -1 for x. So we have log base 2 of -1 squared minus 4 equals log base 2 of 3 times -1. Don't work too far ahead on this one, just to let you know, we're going to run into a problem. Okay, if we do this simple math, we still have log base 2, but then we have -1 squared, which is +1, minus 4 gives us -3. And we have log base 2 of 3 times -1, which is -3. Okay. Don't write anything else after that for now. Huh? There is a problem right now I'm about to tell you about. So on the surface, it doesn't look like there's a problem, right? It looks like, well, -3 equals -3 will be our next line. And that's a true statement, so it worked. Here's our issue. Take a minute and everyone grab your calculator. So if you look at your calculator, I'm going to show you a trick that you probably wish you would have known for the work we did last week. If you press math, which is just below the alpha button, it brings up this list of functions. You're going to scroll all the way down to the bottom, or almost all the way to the bottom, where it says log base, and press enter.
Wow.
That's how you can find the value of any logarithm. So now we can plug in, what we're looking at right now is log base 2 of -3. So is this what you get on your screens?
Yeah, I was like, what's a Godo?
It's go to.
Well, they had a space.
Yeah. Well, I mean, you're right. Texas Instruments apparently doesn't know how to program a space. Okay, so it says error, non-real answer. The reason that it does that is this. You don't have to write this if you don't want to, just look. If you have log base 2 of -3, what question is this logarithm asking? 2 to what power equals -3, right? That's the question that logarithms ask. 2 raised to what power equals -3? Yeah, there's no exponent that you can put on a positive number that will end up then giving you a negative answer. Because raising 2 to a power just means you're multiplying 2 by itself over and over. 2 times 2 times 2 times 2 times 2. You keep doing that, you're never going to end up with a negative number. You're just multiplying +2 by itself. Even if we were to use a fraction as an exponent, that would just end up giving us a smaller positive number. If we use a negative exponent, that's just going to give us a fraction, but it'll still be positive. It will never turn out to be a negative number. So what that means is in a logarithm, in this spot right here, you cannot have a negative number. So make a note of that. These numbers cannot be negative. So because when we plug in x equals -1, it gives us a negative number where we're not supposed to have one in a logarithm. X equals -1 does not work as a solution to this equation. So we mark it out. So even though it looks like it was going to work, -3 equals -3, that's a true statement. Because it's negative, and we know now that you can't have a negative inside a logarithm like this, x equals -1 does not work as a solution. Even if just one or the other were negative, you would still have to stop and say that's not a solution. It just worked out this time to where both of them were negative. But even if just one or the other is negative, you can't keep going after that. So when you guys work these problems, this is what I'm looking for. I'm looking for, you've worked the problem and got your answers for x, but then you've also checked them, and I can see which ones you're saying works because you've circled it and which one doesn't work because you've worked it out. It's also possible for these problems that neither one of the solutions or neither one of the answers that you get will work. Or it could be that both of them will work. Or like this one could work and one doesn't. There's not always like a set, there's always going to be only one answer and one doesn't work. It could be that they both don't work, could be that they both do work. You just have to check every answer you get. Questions on this one? All right, let's look at example number 2. Log base 4 of x squared equals log base 4 of negative 6x minus 8.
I have a question. Will both the logs have the same base pool?
Yes, they have to have the same base in order for you to use this property. If they don't have the same base, then you can't do it. Yeah, good question. Okay, so because these two logarithms have the same base and they're set equal to each other, we know that x squared has to be equal to negative 6x minus 8. So the way that we're going to solve this is by setting those things equal to each other. X squared equals negative 6x minus 8. So just like in the first example, I see that we have an x squared term and we have a term that has just x to the first power. That should tell you that you're going to have to factor in order to solve this. In order to factor, everything needs to be on the same side of the equal sign and have it set equal to 0. There's a couple different ways you could go from here. It's just whichever one you prefer. My first instinct is, well, first of all, you have to keep the x squared positive. In order to factor, the x squared term needs to be positive. So if I were to move the x squared to this other side, it would become negative because I would be subtracting it from both sides. So instead, I'm going to leave the x squared on this side, and I'm going to move both of these other terms over there. So I'm going to add 6x and add 8 to both sides in the same step. So we get x squared plus 6x plus 8 equals 0. Okay. Don't write this. Just watch. There is another way that you could do it. Like pretty much everything in math, there's more than one way to work things. I want you guys to do whatever you feel comfortable with. So if your first instinct was to just subtract x squared from both sides, here's what that will look like. That's not wrong to do that. So you're going to end up with 0 on this side, negative x squared minus 6x minus 8. Now you've done it, you realize my x squared is negative. I can't have that in order to factor. So you're just going to multiply both sides by -1. -1 times 0 is still 0. When you multiply -1 by each term over here, all that does is change the sign. So you get a positive x squared plus 6x plus 8. So really it just took one extra step. Now we're in the same position as over here. Okay, so don't freak out if you, just whatever your first instinct is on how to start a problem, try it and you can usually work it out. I'd rather you do that than just be stuck or not know what to do. Okay, now we can factor. So we factor into two sets of parentheses. We know that x goes at the front of both of those sets of parentheses. Then we're looking for numbers that multiply to be positive 8 add to be positive 6. 4 and 2. So plus 4 plus 2. So you can skip some steps and just go straight to x equals -4, x equals -2. Or if you want to do these extra steps, that's fine. Set each factor equal to 0 separately. And then solve for x. So subtract 4 from both sides. That's what gives us x equals -4. Subtract 2 from both sides here. That's what gives us x equals -2. I feel like I'm writing straight on this paper, and then I look at my screener up there and it's crooked. Maybe my projector's crooked or something. I don't know. It's infuriating. Insane. Okay. So we have our answers for x, but we don't know for sure if they actually work as solutions. We have to go back to the very first line of our problem and plug these values in for x.
Wait,
So-
but since they're negative, what?
Yeah, it wouldn't work.
Well, we don't know that for sure, because it's not just x right here, it's x squared. It's not just x right here, there's other stuff happening too that could possibly make it positive.
Okay.
So plugging in -4, we've got log base 4 of -4 squared equals log base 4 of -6 times -4 minus 8. So yes, I would say it is a red flag that it's a negative answer. So just keep your guard up as you're working and keep a close eye on things. But right now what's happening is this is not just log base 4 of -4. This is log base 4 of -4 squared. So if we actually do that math, yeah, -4 squared is a positive 16. So we're in the clear. On the other side, we have log base 4 of, then we have -6 times -4, which is a positive 24, minus 8 leaves us with a positive 16. So also in the clear on that side. So even if it looks like it's not going to work, you need to at least do this first step of doing the little bit of math there. And then, like in this case, it changes to make it positive. So we can go on to the next step, which is just that 16 equals 16 is a true statement. So x equals -4 does work. We can circle that as a solution. Really quickly, let me tell you, you should always get to a point where you have a true statement as your last line of checking. If you get two different numbers here, like 15 equals 16, then you need to go back to your original work and see if you've done something wrong. The only thing that should stop you from saying a number is a solution is if, like in the first example, you end up with a negative where you're not supposed to have one. Because see, even this one, even though it doesn't work as a solution, would have ended up with -3 equals -3, which is a true statement. But we know that because it's a negative, where you can't have a negative in a logarithm, that's what stops us from using that as a solution. If you get two different numbers here, that means you've done something wrong in your original work. Okay, just wanted to tell you that real quick. Let's check x equals -2. So again, we're going to look very carefully because we do have a negative number. We want to make sure that we don't end up with a negative where you're not supposed to have one. Plug that into the first line of the equation. Log base 4 of -2 squared. -2 squared is +4. So we're okay there. Log base 4 of -6 times -2 is +12, minus 8 is also +4. We don't have any negatives right there, so we can go on to the next step, which is just that 4 equals 4. So -2 also works as a solution. Questions on example 2? I have one more example for the front page. It's much shorter than the first two. So if you have even a little bit of room at the bottom, you can probably make it work. If not, you can use the back, it's fine. And we'll take a break after this third example. Example 3. Log base 3 of 5x minus 1 equals log base 3 of x plus 7. So first step is checking to make sure the bases are the same. Both of these logarithms have a base of 3. So we know that 5x minus 1 has to be equal to x plus 7. 5x minus 1 equals x plus 7. Any guesses as to why this one's going to be shorter than the rest? Say again. Already factored. Yeah. I see what you're trying to get at. There's no x squared term. So we don't have to factor in order to solve this one. So when we have to factor, you have to get everything on the same side of the equal sign. If you don't have to factor, which we don't have to in this one because there's not an x squared, all you have to do is get all the x terms to the same side with everything else on the other side. So I'm going to subtract x from both sides. That's going to cancel out these x's over here. And that's going to make my x term be only on the left side, which means in the next step, I'll want to get rid of this minus 1. I'm going to go ahead and just do that in this same step. So I'm going to add 1 to both sides to get rid of this 1 over here. So what we have is 5x minus x, which is 4x, and 7 plus 1, which is 8. Now to get x by itself, just divide both sides by 4. We get x equals 2. Much simpler than the first two. We still do have to check this answer though. So we need to plug x equals 2 back into the very first line of the equation. Log base 3 of 5 times 2 minus 1 equals log base 3 of 2 plus 7. So one thing that's a common mistake when students are working this problem is that you go ahead and just set this equal to this. That's what we did when we were working it out. That was our first step. But when you're checking these numbers, the first step needs to make sure that there's no negatives where there's not supposed to be negatives. So you can't just leave the logarithms off at the very first step. It still stays log base 3. 5 times 2 is 10, minus 1 is a positive 9. So we're okay there. And then obviously 2 plus 7 is not going to be negative. That also gives us a positive 9. So 9 equals 9. That means x equals 2 is a solution. So the reason I say that about not leaving the logarithms off right away is that let's just say whatever x value we plug in, this ends up being log base 3 of -9 equals log base 3 of -9. If you leave the logarithms off and you just say -9 equals -9 in the very next step, you might forget that these used to be inside of a logarithm, and you might just say, yeah, that works, so my answer does work. Because you're not seeing it within the context of a logarithm. That's why you leave the logarithms at first to make sure there's no negative where there's not supposed to be a negative. Then you can move on to leaving the logarithms off. The bases is what is allowing us to use the property. The only thing they're serving right now is to make sure that they're the same. Then we can just use the property. If they're not the same, then we can't. But other than that, yeah, you don't really include those numbers anywhere when you're working. Okay, let's take a short break and then we'll start on the back page of the notes. All right, back side of the notes. If the base of a logarithm is not written, it is understood to be 10. So up until now, in all of the logarithms, you've had a base written. Let's say now you're given something that looks like this. Log of 100. There's no base written. Well, it's understood to be log base 10 of 100, which is 10 to what power equals 100? 2. Yep. So it's similar to a lot of things in math where the most common used thing is shorthanded, just like square root. There's no 2 written anywhere, but we still know it's the square root. Because if it weren't the square root, it would have a different number, like cube root, fourth root, and so on. But because there's not one written, it's understood to be the square root. For logarithms, if there's not a base written, it's understood to have a base of 10. Okay, so that'll come into play some, and then we have 3 more properties that we're going to look at. The first one is called the product property. So let's say we have log base b of a times c. Log base b of a times c. The product property says this can be written as log base b of a plus log base b of c. So you can split that logarithm into 2 separate logarithms with the same base, and you split a and c up into each one of those logarithms and you add them together. That is the product property definition. Here is an example of how we will use the product property. Log base 2 of 5 plus log base 2 of 6. So the way that we're going to actually use this property is kind of backwards from how the definition is written. The definition shows us one logarithm being split into 2. The way that we're going to use this property is by having 2 logarithms that we want to write as 1. So because these logarithms have the same base and they're being added together, we can write this as log base 2 of 5 times 6. Okay, if we wanted to go one more step, we could say this is log base 2 of 30. So the reason that we're going to use this to combine two logarithms into one is because the property on the front page, we were able to use it because it was one logarithm set equal to one logarithm. We didn't have log plus log equals log. In order to use this property, we have one logarithm set equal to another logarithm. So we're going to use the product property to make sure we only have one logarithm on each side. So if we have two logarithms with the same base being added together, we can combine them into one using this property. Okay, quotient property. Log base b of a divided by c. This property says you can write this as log base b of a minus log base b of c. So for example, if we have log base 2 of 5 minus log base 2 of 6, which I just made these numbers up just as an example, by the way. But again, the way that we're going to use this property is pretty much backwards from how the definition is written. We're going to use it to take two logarithms with the same base that are being subtracted. We want to write this as one logarithm. When we do that, the base stays the same. So it stays log base 2. And then whatever number comes first becomes our numerator. Whatever number comes second becomes our denominator. So this is log base 2 of 5 over 6. There's not really a simpler way to write 5 over 6, so we're going to let that be our last step. Okay, power property. Log base b of a to the c power. So this time c is an exponent on a. This property says that whatever that exponent is can be moved down in front of the logarithm. So this becomes c times log base b of a. Okay, an example of how we're going to use this property. Let's say we have 5 times log base 2 of 6. So in order to use any of the other properties that we've already talked about, you can't have a number in front of these logarithms. So all on the front page, there were no numbers in front of these logarithms. And now looking at the product and quotient properties, there's no numbers in front of these logarithms either. So if we end up having a number in front of a logarithm, we are going to use the power property to get rid of it. So the power property says I can write that 5 so that it's an exponent on the 6. So now I've gotten rid of that number in front of the logarithm by moving it so that it's an exponent now. If you wanted to do 6 to the 5th power in your calculator, you would get 7,776. Okay, y'all ready to work some examples? We'll go ahead and label this example 4, since we did 3 on the front page. So example 4. log base 6 of x plus log base 6 of x minus 9 equals 2. So what sticks out to me first is that we have two logarithms that are being added together. So first you need to check that they have the same base. Both of these logarithms have a base of 6. And we want to rewrite these two as one logarithm. So when we do that, the base stays the same, so it's still log base 6. And because they're being added together, that means we're going to multiply x times x minus 9. Equals 2. Okay, let's go ahead and multiply here by distributing the x. So we have log base 6 of x squared minus 9x equals 2. Okay, now we're coming across something that we've not had yet so far today. That is a logarithm on one side set equal to just a number. All on the front page, we had a logarithm equal to a logarithm. Now we have a logarithm equal to a number. When this happens, your next step is to change this to exponential form. So just like, you don't have to write this, but let's say we had something like this. If we wanted to solve this and change to exponential form, this would be 2 to the 7th power equals 5. That's obviously not a true statement, but I'm just showing you that up until now, we've done pretty basic logarithms when we're changing to different forms. We can still do the same thing, even though this looks a little more complicated. So if you want to use the loop trick, you start at the base, which is 6. Draw a counterclockwise loop around to x squared minus 9x. So when we write this in exponential form, you follow the loop. 6 squared equals x squared minus 9x. That whole thing. As you're working these, once you don't have any logarithms left in your problem, that's when you start solving for x. So I know that I have x squared and a term that has just x. That should tell you that you're going to have to factor in order to solve. So to factor, you want everything on the same side. You want your x squared to stay positive, which it is already. So I'm going to subtract. I'm going to go ahead and call 6 squared 36 if everyone's okay with that. So I'm going to subtract 36 from both sides. So that I have 0 equals x squared minus 9x minus 36. Once we've done that, we can factor into our two sets of parentheses. We know that x goes to the front of both. Then we're looking for two numbers that multiply to be negative 36 and add to be negative 9. Yep, 3 and 12 works. I think you had your negative on the wrong one. Negative 12, positive 3. If you struggle with this part, what I like to do is I take the number that we're trying to multiply to get, which is negative 36, and I list out my factors. So 6 and 6 comes to mind first. One of them would have to be negative, but if you add these together, you don't get negative 9, you get 0. So those don't work. We've got 4 and 9. Try to make one of these negative. Either way you go, you're not going to end up adding to be negative 9, so those don't work. And then 3 and 12, honestly, is my last thought when I'm thinking of factors of 36. But that is the one that works, 3 and negative 12. Okay, so from this point, remember you can say x equals positive 12, x equals negative 3, or you can do the steps where you set each factor equal to 0 and solve in order to get those answers. Add 12 to both sides gets us x equals 12. Subtract 3 from both sides gets us x equals negative 3. Okay, so we have our answers, but we have to go back and check. When you go back and check, you have to go all the way back to the very first line of the problem. You can't skip to right here and plug in your x value. You can't even skip to the second line and plug in your x value. You need to plug in to the very first line of the problem. So let's check x equals 12. We've got log base 6 of 12 plus log base 6 of 12 minus 9 equals 2. Any math that is within a logarithm, you need to do that first before using any of the properties. So we need to do 12 minus 9 first. It's obviously not going to end up being negative, but if it did, then that would stop us. So we have log base 6 of 12 plus log base 6 of 3 equals 2. After you make sure there's no negatives where you're not allowed to have a negative, then all you have to do is follow the same steps that you followed when solving. So the step that we did when we were solving was to combine the two logarithms into one. So if we do that here, we have log base 6 of 12 times 3. The next step that we did when we were solving was we changed this to exponential form. So we get 6 squared equals 12 times 3. Well, 6 squared is 36, and 12 times 3 is 36, and 36 equals 36. So x equals 12 is a solution. We can circle it to show that we checked it. It is a solution. Then we check x equals negative 3. So the very first line of the problem, we have log base 6 of negative 3 plus log base 6, negative 3 minus 9 equals 2. So immediately, I see this negative 3. It's not being squared. It's not being multiplied by another negative number that might possibly make it positive. It is negative and it is staying negative. So that immediately tells me x equals negative 3 cannot be used as a solution. This number also ends up being negative. Negative 3 minus 9 gives us a negative 12. Now, let me clarify. You don't have to, don't write this. It would probably confuse you later if you look back. But because both of these are negative, and then we say, well, let's use the product property to say this is log base 6 of negative 3 times negative 12. Now we have two negatives being multiplied together to get a positive 36. Okay, but we had to use a property of logarithms in order to make this happen. We're not going to do this. Before using any properties, if there is a negative number in a logarithm, that stops you in your tracks. You can't go forward. If there is a number written within the problem, like it was on number 2, example 2, where you had -4 squared, because that's what the problem, that's how it was written. It was written as x squared. We didn't have to use any property to make this become positive. It became positive because of how the problem was written. So that was fine. But in this one, we would have to use a property in order to force this to become positive. That's a no-no. If it becomes positive on its own because of how the problem's written, you're good to go. If you have to use a property to force it to become positive, it doesn't work. Okay, I would like us to stop right here for today because I have 3 examples left, but I would rather save those for next time to spark your memory before I give you practice problems. So I know you guys still have a lot of time left today. If you have work for other classes, you can do that, or just find something to help you be productive.